You got 4-bit encryption, binary math, sign numbers, sign of magnitude, 1's complement, 2's complement. Huh? No, we didn't. I did it in another class, but I put it into the keynote for this class. But since it's in your keynote, you must be responsible for the information. Isn't that like the go-to move for any teacher? Like if it was covered in class? I just flipped through those slides. It's been covered. I'll move them back to the class they're supposed to be in. All right, so let's write this thing. Have I started the project yet? Oh. What did you think of the assignment, Charlie?
It's pretty hard. I sat on my computer for so long. I still can't get a complete grasp of the inheriting model using the.
So did anybody find the assignment like easy? It's like I almost gave you the entire yard algorithm to do over the weekend. I thought that would be reasonable. Like, oh, I'll give them an easy weekend and just have them do the parsing piece. Let's see if I thought about this the wrong way. So we're gonna go ahead and so we're gonna read in something from our interface. I haven't built the interface at all, if I remember correctly, right? So we're gonna have a little text box in our interface that's going to read some stuff in. So let's get rid of our hello world. We'll just throw our who? Oh, I didn't. But I did change. Okay. I did change something on here. So, but you're saying this one didn't work either. Let me. Well, that wouldn't make a difference.
And mine wasn't allowed to run the program.
But it had in the past.
Yeah.
Okay, so I didn't fix it for you, and I broke it for you. Oh, excellent. Let's see. I wonder why. Because I think I was using API 26, which is the latest, but then I would have expected it to work on. So you didn't have an interface thing that could show up like this? These are the APIs I have installed. Do you do it on that laptop there?
Yeah. I don't know. I thought it was just something going on with Android, but it's been updating for like.
Oh, I see. All right. I will try to look at it today. I'm sorry about that. But in this case, you could have just put it into a string because, I mean, all we're reading in is from one text box in this. But as we get more complicated here, we'll definitely need more. All right, so let me put a vertical linear layout in here. There's that dude. I'll go ahead and just throw in a plain text thing because we're going to be entering in different stuff. We're going to say enter expression. We'll center that guy. We'll take the text that's currently in there out. And we're going to name this guy input ET. Okay, then we'll just give ourselves a button. And this guy will say click me. All right, let's go write the handler for that button. So this would be a public void on click me button pressed view v, and we'll just make sure this is working. and we'll go back here. We'll hit hook up its on click. All right, let's go ahead and run this dude. Okay, that is connected. Okay, so button is working. All right, so now let's write our parser. So for the homework, you're supposed to read in a string that looks something, you know, like 123 plus 4 divided by 8, that kind of stuff. Did I say you could assume there's no spaces? Okay, well, you could have assumed there was no spaces, but I'll write it both ways. So it would be easiest if you assume there's no spaces. Otherwise, you'll have to write a little function to remove spaces. So we'll go ahead and write the function to remove spaces anyways. So this is really a good exercise to go back to normal problem solving, where, you know, historically, well, kind of looked like you were looking for power tools that would do this job, and string tokenizer is something we've looked at that would actually have made this not too bad. But, you know, in any case, even if you didn't know about a particular power tool, you could have just written these individual pieces. They're just little functions that are going to do something. So let me go ahead first, and we'll just write a public string remove spaces. Actually, I'll make this guy private because we don't need it outside of here. So private string remove spaces, we'll take a string s as a parameter, we'll create a new string answer. All right, and we're just going to go through and keep everything from s that is not a space, right? So we'll say for int I is equal to 0, I is less than s dot length, I plus plus. If s dot char at I is not equal to a space, then answer is equal to answer concatenated with s dot char at I. Return answer. So that'll remove spaces, right? Okay, so taking the string, create a new string that we're going to build up here, go through our existing string. For every character we see in there that is not a space, tack it onto our answer string, ultimately return our answer string. We can go ahead and test this real quick. So we will concatenate onto the, well, I need to give myself access to that input button. So we're going to say, what is this, edit text, input et is equal to the edit text version of this dot find view by id, r.id.input et. All right, and then we'll just go ahead and call this dot remove spaces on input et dot get text dot toString. All right, so now we'll test this guy, but we'll throw some spaces into our function and make sure this guy is removing the spaces. But when you wrote this, you could have assumed there was no spaces. You didn't have to do this part of it if you didn't want to. 123, we'll put a bunch of pluses in there. Plus 8 minus 2 divided by 5. Click me, and there's our function without spaces. All right, so we're good with that? Okay. So now we want to, we'll do this the hard way. We want to walk through this, this string collecting numbers and collecting operators. All right, so we know we're going to have a number first, right? So we're going to keep walking through, and as long as I'm looking at digits, as long as I'm looking at some value between 0 and 9, I want to collect it. And as soon as I run into something that's not a 0 through 9, that must be an operator, right? Therefore, I want to go ahead and store. So I'll just print out my number right now saying, here's my number. I'll start off with a new number. So we'll write this in little pieces. So we'll say private. For right now, I'm just going to make it void. We'll call this guy parse string. This will take a string s as a parameter. Okay, so I'm going to, now we know all operators are 1 character long, correct? Okay, so I'm going to create a little string called cur_number, and we'll start this guy off as the empty string. We're going to have our normal for loop that's going to loop through every value in my input string. So for int I is equal to 0, I is less than s dot length, I plus plus. All right, so this is going to go through every character in my string. Each time we go through there, we need to say, am I currently looking at a number? Am I looking at a value between 0 and 9? Okay, we can do this a couple different ways. If you happen to know about the character class that has a isDigit function in it, you could use it. You can ask that question. Otherwise, we can go back to our nice little string map thing. That's bad. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And actually, why don't we just call this guy digits? All right. So we know that we're looking at a digit if, when I look for the index of the current character, it gives me something other than -1. Then I must be looking at a digit. Okay. So if s dot, well, if digits dot index of, so we're going to search for a character in there. The character we're going to search for is the current character in S. If that guy is not equal to -1, if it gives us something other than -1, that means the current character we're looking at is a digit. And if it is a digit, we're going to go ahead and tack it on to our cur_number. Make sense? So we'll just keep building up our current number, like 1, then a 2, then a 3. Okay? Now, if it's not a digit, I must be looking at an operator. So I'm going to go ahead and just do a system.out.println. Found a number, cur_number. Then I'm going to set cur_number equal to the empty string in preparation for the next number. And then I'll say system.out.println found an operator s.char at I. And we'll just keep trucking. All right, so if I'm looking at a digit, build up the current number. Otherwise, I must be looking at an operator. Therefore, I'll say, I found a number. The entire number was what I've collected up to this point in curnum. Then I'll go ahead and zero out curnum in preparation for my next number. Finally, I'll say, I found an operator because I'm currently looking at that operator. So I'll print that out. And then we'll move on to the next iteration through the loop. When this loop has ended, I might still have something inside of cur_number, right? In fact, I probably will have something inside of cur_number. In the example of if I just had the string 123 and no operators, I would have never hit something that was not a number. So curnum currently would be, or cur_number would currently be equal to 123. I would need to spit it out. Okay, if I had something like +8, I would have read the 1, then the 2, then the 3 into cur_number. I would hit the plus sign. At that point, I would spit out, I found the number 123. Then I would zero that out. Then I would say, I found an operator, the plus sign. Then I would start collecting the 8. At which point, when I exit this for loop, I should have my final number inside of cur_number. So I'll do one last print. And I don't even need to zero out cur number because we're done. All right, so that's the parse string function. So now what I should be able to do here is I'll just do this in a couple of variables. So I'll say string value without spaces is equal to this dude. Okay, then I'll go ahead. I don't need the println here because my parse thing does the println. So I'll say this dot parse string, and I'll pass it my value without spaces, and it should go through and it should give me the one found a number 123, found an operator plus blah 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 blah. Okay, so let's go and test this guy. So we'll do 123 minus 8 divided by 2, put a bunch of spaces in here, times 4. So I should, my output should be found a number 123, found an operator minus, found a number 8, found an operator divide, found a number 2, found an operator times, found a number 4. That's what we'd expect this guy to give us. So there's our found a number, those pieces there. All right, so that would have been the more difficult way of writing it. I realize I make it look easier than it. Good.
If you didn't, let's say, for whatever reason, you didn't have a final number, would you just say found a number and it was 0?
Yeah, but if you have legitimate input, you would always have a final number. For instance, any bad input would be, well, if you had like 123 plus, you would have nothing in cur number, but you also, that's not legal input, right? So you'll always have a number if you have legal input. So you can either assume you have legal input or not. In which case, if you want to check if you have illegal input, you can always ask the question here. If cur number is the empty string, then, or if its length is 0, they gave you an illegal input. That would be not the only catch-all, because they could also put smiley faces and stuff like that in there. But if we're assuming they give us legal input, you would never have something without a final cur number. All right, so does this version of parse make sense? I know we haven't put it into our inheritance model yet, but we're getting our pieces. So we have all the pieces that we need to create those dudes. Okay. Now, I'll just point it out here. So this is kind of I realize this maybe isn't the easiest logic in the world, but as we went through this isn't that bad, right? All right. So one thing that many of you might have done is you might have been looking for an external solution rather than just saying, okay, this isn't that big a deal, I'll just write it real quick. Or maybe not real quick, but I'll spend some time writing this because I have the capability of writing that tool. This isn't 3,000 lines of code or something. It's just, we're walking through a string. We've been doing string manipulation stuff for a while, but it might not necessarily be the first thing that comes to your mind when you're solving problems. Right? So maybe start relying on yourself a little bit more, because I'm sure some of you dove into Google. Okay, some of you dove into regular expressions, even though I've never introduced them. But regular expressions are cool. Don't get me wrong. Okay, but they're overkill for this problem. Regular expressions are great for things like validating an email address. Stuff like that, validating a website, a URL, making sure somebody's entered in a legal thing in that format. It's an overkill for something like this. Okay, so let me show you. Say this again. No, we haven't, because we haven't put it into our objects yet. But pretty much as the homework assignment, because I think, didn't I already write? Yeah, I already wrote RNQ. So yeah, it really was, because we can just take the Here, we'll just finish the assignment real quick, and it's only a couple more lines of code. So we have our queue. So I'm going to go ahead and make my queue global. And we'll say private queue. We'll go ahead and fill it there. And notice we have two versions of enqueue, one that takes an int, one that takes a char. So I'll get rid of these dudes right here. All right, then in here, I'll still print it out just for our own vision right now, but I'll go ahead and say, since I found the number, I'm going to say this.queue.enqueue. I'm going to give it an integer. That is integer.parseInt of cur number. Then I'm also going to add my char here, which is s.charat_i, which is going to be my operator. So I'll go ahead and enqueue the integer version of the current number, and I'll enqueue the char version of my current operator. And then down here, I will enqueue the that dude there. All right, and then, so that would be the homework assignment. Did we have a display method in our queue? Does our node know how to display stuff? Do we have get payload? Set next node. Okay, so we can go ahead and grab the payload quickly from, actually, hold on, I need to look at my op node and my, so we have get payload in my op node as well as my other one, so we'll just print those guys out. So just to prove that it worked here, let me look at my queue. Are we keeping track of whether it's empty or not? We're not. So what I'll go ahead and do is I'm just going to throw a function in here. Public boolean is empty. And this guy should return true if we're dealing with the empty list, which means front would be equal to null. So, or the empty queue. So a front is equal to null, queue is empty. All right, so we'll just add that little ability to queue. And then out here, I'll just create a quick while loop. So while this dot queue dot, while that guy is not empty. So really the homework assignment is done with what we have up here. Now we're just proving our queue got empty, filled up with the right stuff. I'll do a system.out.println. And we'll say this.queue.dq.getPayload. All right, so notice that right now this guy's giving me an error message. So really what we need to do is we need to say node n is equal to this.queue.dq. Then we're going to say if n is an instance of, what is it called, num node? If it's one of those guys, then I'll want to say, I'm going to steal this line. This is the num node version of my DQ, and I'll call get payload on that guy. Else, this is the op node version, and I'll call get payload on that guy. We could actually create an abstract function inside of node so that we wouldn't have to differentiate there since we know that both of them have a function called get payload. I'll show you that in a few minutes. But this will show the output of our queue, proving that we entered those separate guys in there. (123 plus 8 divided by 2 times 4). What row? The queue is not empty. It says could not execute method on click. Oh. This is what I call it. Well, I did call it opnode. And this QDQ gives me a generic node. And opnode extends node. Numnode extends node. It doesn't like me casting those. Cannot be cast. It doesn't like what I'm doing right here. It doesn't like me turning this guy into, maybe it just doesn't like it in place. So if I say numnode temp is equal to this.q.dq, like that, and this will be the numnode version of that, then I should be able to say temp.getPayload there. And this will be the opnode version of that. And then I'll get payload there. Let's try that guy. Doesn't like me casting. Why? Oh, I'm calling DQ multiple times. I don't want this .dq. What I had before would have been fine. This is maybe a little cleaner anyways. I already have my DQ'd value. It's called n. When I was DQing an extra time, I was always getting the opposite of what I was trying to cast. So here, let me just back this. I was saying, give me my number, then give me my operator, but cast it to a number. Otherwise, I would say, give me my operator. That's what I was getting right here. Then that guy would be an operator. Then I would say, go ahead and grab me the number and convert it to an operator. I didn't need to DQ a second time here. I'd already DQ'd right here. So this should just be n. And this should just be n. Now he'll be happy. All right, so there's our outputs, 123 plus 3 minus 8 times 4. And those guys are stored inside of the appropriate kinds of containers. Go ahead.
This is going back a little bit, but can you define what a global variable is and how that's different than a singleton?
Okay, so I've made this guy, Q, global, which means that it's accessible, its scope is only inside of main activity. Where a singleton would be written in another class and would be accessible by any of the other classes in our program. Does that make sense? Okay, so up to this point, this would have been the homework. This is just proof that we filled our queue up with the right kinds of stuff. Okay, so now let's write the easier version of parse string. So we'll call this guy parse string 2. And actually what I can do here is I'll just grab all that logic right there. And I'll just create a little function called private void test queue. I'll just throw it in there. So then at the end here, I can just say this dot test queue. And that'll test to make sure it got filled up with the right stuff. So I just threw that logic here. That way I can test the queue from both of my versions of parse string. We'll test this real quick. Just make sure we didn't break anything. I think we're fine. 123 plus 3 minus 7, whatever. All right, so there's our output there. All right, now at the same time, we can also go ahead and we can dump some of our output verbiage here for when we found operators and we found numbers. All right, so in the end, that's our final version of homemade parse string. Now we're going to create a version of parse string that uses the string tokenizer. Private void parse string toke. This guy will take a string s as a parameter. I'll go ahead and create a string tokenizer st. This is going to be a new string tokenizer, passing it s, and then passing it my delimiters. So my delimiters are going to be plus minus times divide. Why is that typing up there? Plus, okay. And with parse token, we wouldn't even need to remove the spaces because we can go ahead and just call trim on each thing that we read in. So I'll go ahead and say while st dot has more tokens, I'm going to give myself a string temp here to read a token. We'll say temp is equal to st.nextToken.trim. That'll take any spaces off of it. So now temp is going to hold something that is either an operator or something that is a number. So I can go ahead and do my little thing here where I can say string digits is equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If this dot, if digits dot index of, and I pass it, actually, I want to do plus minus times divide in this because those are going to be the ones that are guaranteed to be single characters. So we'll call this ops. So I can say ops dot index of temp. If that guy is equal to a -1, that means I did not find a operator in that string. Therefore, it must be a number. So I'll say this dot q dot nq new num node, and I'll pass this guy integer dot parsing of temp. Oh, it doesn't take in a I don't have to build my num node. This guy just takes in an integer. We wrote nq to take in an int, not a node. So nq will take in the integer. Otherwise, this .q.nq, this guy takes in a char, so the char would be temp.char at 0. So that's the other version of parsing. And then I can go ahead and say this dot test q like that. And now I don't need to get the value without spaces. I can just pass directly to parse string, my string with all the spaces and stuff. And this is parse string 2, or parse string toke that we just wrote. So the tokenizer version of parse string will pass in my string however we entered in, with or without spaces. It's going to use the tokenizer to tokenize S on these delimiters, plus, minus, times, divide. So we'll divide it up into individual tokens that might have some extra spaces in them. Give myself a temporary variable. I have a collection of my known operators. Now, every single time we burn a token, st.next token, it gets permanently removed from my, so think of this like a queue, remove front. All right, so it'll get removed. So as long as there's still more tokens in there, grab the next token and trim it, so get extra spaces from either side off of there. Then I'll ask the question, if when I search in ops for the current value in temp, if it's not found, that must mean that it is a number. Therefore, I'll NQ the integer version of temp. Otherwise, it must be an operator, so I'll NQ the char version of temp. That make sense? Now, up here real quick, and then up here real quick, when I am asking whether ops.index of temp is equal to -1, in this case, temp is a string. That means there's two versions of index of, one that takes a char and one that takes a string. If you didn't know about the char one, you would say, oh, well, if this is an operator version of a string, the operator would live at bucket 0. So you could say dot char at 0 to check only the first character of that string to see if it's an operator. Otherwise, you'd be looking at a number like a 2 or a 3 or something like that. Go ahead.
Yeah, I was just worrying about the L with the char at 0. Basically, when you get to that L, there's only one element in that.
Yeah, but I have a string that looks like, so let's say it's a string that looks like that.
Yeah.
Well, my NQ for op nodes takes a char as a parameter. So I need to give it the char at that position, which will be that guy. That is the character that lives at bucket 0 of that string. Make sense? All right, so let me run this real quick, make sure that the tokenized version works. 123, we'll give it some crazy spaces, -2 plus 8 times 4. And there is, oh, one last thing for string tokenizers. Notice I just got my numbers out of this. I wrote all the correct logic, but when I create that string tokenizer, I need to tell it that I definitely want it to return delimiters as well. Otherwise, it just splits it on your delimiters. So there's a third parameter there for return delimiters. Now, it'll operate the exact same way we had it operate before, but it'll also spit out tokens that are equal to the delimiters. So there's our 123 plus 4 times 9. That make sense? Okay. So, questions about any of the stuff we just did there? Do you think the tokenizer version of this is actually easier, or was that harder to follow? Yeah, I mean, I'm not sure it's necessarily cleaner. I mean, lengthwise, they're pretty similar, right? In fact, actually, we might be a little shorter in parsing it by like a, one line or something. But regardless, was this logic that bad?
It's better.
And that's our homegrown one. That's the one we just wrote using our own brains, rather than built-in tools or regular expressions. Okay. So now we have our numbers in the format of a queue, right? So now we need to see, how does the shunting yard algorithm work? All right, let me shrink this down just a little bit. All right, so shunting yard algorithm has an operator stack. So we have 3 different things that we're working with here. We have our input queue. We've built that piece, right? Then we have an operator stack. So as we are grabbing stuff from our queue, so as we're dequeuing stuff, if what we're dealing with is a number, we immediately add it to the end of our output queue. So this is an output queue. This is an input queue. Now, you could actually think of this as a queue or a stack, but we're always adding stuff to the end of it. So depending on how you want to process that guy, it's going to work, I guess, a little different. So I would think of this as a queue. So we have a queue here. We have a queue here, and then we need a stack for our operator. So we're going to have a stack that can hold a collection of op nodes. Okay? So now, if we scroll down here a little bit, different operators have different precedences. Okay? And we know that from the rules of math, right? All right, so a multiplication and division, we're leaving powers out of here, even though it would work the same way. But multiplication and division are more important than addition and subtraction, right? So those get precedence when we are solving a math problem. So, excuse me, if I have a problem, precedence. Pretty surprised I got that right the first time. So if I have 123 plus 4 times 2, the order this happens is 4 times 2 is 8, and then 123 plus 8 is 131. That's the order those things would happen, even though as a human we read this left to right. Does that make sense? So typically, if we're not clear at order of precedent, we might go ahead and we might throw parentheses or something in here to make things a little cleaner. And shunting yard actually does support parentheses. You can make parentheses work as well. But we'll start with just the clean left to right version of this at first. Okay, so as we're walking through, this is going to be our first token. It's a number. We'll go ahead and just throw it onto. All right, so if we kind of walk through here, they give us an example up here. So assuming we're looking at something like this. All right. Now ours are not going to have the powers in it, and we're not going to have the parentheses at first. Actually, we might as well, no parentheses at first. Let's just keep it simple. It doesn't really add anything to the problem. All right, so we won't have parentheses, and we won't have these powers. All right, but we support all the other operators. So as we start going through here, our first token is a 3. So that guy's a num operator, or a num, what do they call it, num node. That guy's a num node, therefore we'll just go ahead and toss him right onto the output queue. He's already there. All right, then we get to an op node. So our next node is an op node. As we dequeue it from our input queue, we know we're looking at an op node, but now we need to ask the question. This is similar to Towers of Hanoi, where we say, is this guy allowed to go onto the top of my op stack? Now, as far as we know right now, we're going to say the answer is yes because the op stack is empty. Okay, so we'll throw them on there for right now. All right, so that's my operator stack. Then I run into my next token, which is a 4. Num node added immediately to the output queue. So my output queue currently looks like this, 3 and 4. All right, then I'm going to read in my next op node, which is multiplication. And since multiplication has a higher precedence than addition, since it is larger, so this is almost the inverse of, it's the inverse of Towers of Hanoi, where only smaller disks could go on top of larger disks. And here, larger orders of precedence can go on top of smaller orders of precedence, but not ties. You'll see that here in a minute. All right, so because multiplication has a higher precedent, we go ahead and push it onto the top of our operator stack. So our stack now looks like this. Multiplication at the top, plus below that. Then we reach the 2. We go ahead and enqueue it to the end of our output queue. Operator stack still looks like this. Then we hit division. Now division has an equal strength to multiplication. All right, and the way we do that in the case of a tie, we operate left to right when we're doing math, right? So if I had a something that looked like this, if I had 123 times 2 divided by 8, something like that, the multiplication and division have the same power from an order of precedent perspective. Therefore, I will do the 123 times 2 first because that's the first thing that occurs left to right. Then I'll take that answer and divide it by 8. Make sense? So that's math we've been doing for a long time, just reminding ourselves of order of precedent. Okay, so now I hit division. So now we look at the op stack and we say, can I push division on top of the op stack? The answer is no, because the guy at the top of the op stack has the same order of precedence as me. So I need to pop multiplication from the top of the op stack and add it to the end of my output queue. Okay? Then I can then ask again. I'll go and try to push the division on again. I'll say, will this fit? Guy at the top is the plus sign. He's got a lower order of precedence, so I can go ahead and toss it in. Okay, so we're only allowed to add it if it has if the guy at the top has a lower order of precedence than the guy we're trying to add. So now our op stack looks like divide followed by addition. All right, so we'll forget about parentheses for right now because we're not tokenizing on those, but parentheses are are open parentheses just gets thrown onto the op stack. Then a 1 gets put under output queue. It's a num node. Now we have our push token onto the stack. We have a minus. Now a minus, yeah, see this one's, this is tougher to go through here because we're ignoring the parentheses. I wonder if we should just include parentheses. Because the idea here is we were allowed to put these parentheses on top of division because parentheses are always more important than multiplication or division. They take precedent over it. So I was able to put the parenthesis on there, but I was also able to put minus on top of there. So it's kind of like a double dip thing, but we'll just keep trucking here. Actually, what I can do, now that we have the general pattern down, let's work with an example that would work in our code. So I'll come to another thing here, and we'll call this shunting yard. And let's just give ourselves a example that doesn't have parentheses in it. So we'll say 123 plus 8 times 5 divided by 2. All right. So now the math for this guy would be 8 times 5, which is what, 45? 40. Divided by 2, which is 20. And then 123 plus that, which is 143. That's what we should get when we're done, okay, if this all works out. So we're going to have our input queue. We're going to have our op stack. And we're going to have our output queue. So our input queue is going to look like this. 123 plus 8 times 5 divided by 2. Each of these are separate tokens, right? They are separate node types. So the very first thing we do is we dequeue the 123. Because it's a num node, we immediately enqueue it in our output queue. Then we go back to our input queue, we dequeue the plus sign. We try to add it to the op stack. Currently the op stack's empty, so we push it to the top of the op stack. Then we dequeue the 8. Because it's a num node, we immediately enqueue it at the end of our output queue. Then we dequeue multiplication. We ask, can I put multiplication on top of a plus sign? Is it more important than addition? It is. So I go ahead and push onto the top of the op stack my multiplication. Then I dequeue the 5 because it's a num node. I enqueue it in my output queue. Then I dequeue my divide. I try to push that onto the op stack. It's not allowed because the top of the op stack currently has something that is the same strength as that. So that means I need to, here, I'll put this back for a second. I just tried to do it and I failed. Now I will pop from op stack and enqueue it in output queue. Then I will try to add the divide again. Dequeue and push works now. Then I will dequeue the 2, immediately enqueue to the output queue. Now my input queue is done. So now the last thing to do is to clear my op stack. So I pop and enqueue. So I will pop the divide and enqueue it in output queue. I will pop the plus and I'll enqueue it in output queue. So now I've completed pre-processing all my data and I have it set up in my output queue in the correct order. Okay, so now we need to process our output queue the correct way. So let's go back in here. What's up? But to write that code as a human being, to walk through this. That's easy for us because we're able to immediately apply the order of operation rules. This guy right here is known as reverse Polish notation. Okay, that's reverse Polish notation. All right, so they don't give an example of that side of it. So now I have my code like this. So now what I need to do is I need to start processing this guy. So let's call this guy the solution stack. Okay, so we're going to pop off the output. We're going to dequeue from the output queue the 123. We're going to push it onto our solution stack.
And 123 is at the bottom, right?
Say this again.
123 is at the bottom.
Well, it's at the top right now, but it will become the bottom of it.
Okay.
Yeah. Okay, so
First in the
Yeah.
queue,
you'll see how it works here. So I popped the 123. I noticed it's a number, so I went ahead and I pushed it onto my solution stack. Then I pop the 8, notice it's a number, push it onto my solution stack. I pop the 5, notice it's a number, I push it onto my solution stack. I pop the multiplication. I notice it's an operator. So I apply that operator. We always apply operators to the top 2 things in our stack. So I need to now apply that operator. So the operator is going to require 2 inputs. I'll just do a little curop thing here. Curry. We'll just call it do math. This will be a function we're going to pass it to. So we're going to have multiplication, and then we're going to pop. So the 5 and the 8 will get popped off there because those are going to be my 2 inputs to that math function. 5 times 8 is 40. This guy will produce a 40. I will then push the 40 back onto here. What happened to my plus sign? Oh, I didn't finish filling this yet. So we hit the multiplication. No, I was doing the right thing. Sorry, I got ahead of myself here. So this is do math. We read in the multiplication sign. Then we pop, get the 40, push it back on. Then we read at the next value, which is 2. So we dequeue it. Because it's a number, we push it onto the solution stack. Then we read in our divide. It's an operator. So the math we're going to do is divide, pop. Now, we're doing 40 divided by 2. So we need, depending on how you're doing this here, you would probably pop, and that would be my second parameter. And pop, and this would be my first parameter. You can write it either way. It doesn't matter. Just when you do your math, make sure you're dividing the second guy by the first guy. And this is going to give us a 20. We push the 20 back onto there. Okay. Now, let's see, what did I get all the pieces? I also need the 40 off of there, right? Let me just back up for a second. Yeah. So we're dividing by pop. So that's going to be 40 and 2. So these guys were both popped off. This is going to produce for me a 20. I'll push the 20 back on. Then I'll dequeue the plus sign. I need to do some math. I'm going to pop. So that's going to be 20 and 123, which is going to produce a 143. These guys were both popped. And then I'll push the final answer back on there. And then we notice our output queue is empty, and the top of our solution stack has our final answer. That make sense? Huh? Okay. So let's do another one of these, because it's really important that we understand this. Let me just steal this slide. Let's do 8 divided by 2 times 3.
So what is that reverse parsing notation? What is that?
That was the format that guy was in, which allowed us to use a stack data structure to do the math. So shunting yard is about getting something that's in this format into reverse Polish. I'll add a 7 to that. That way we have some addition. So this is our initial input. We're going to go ahead and tokenize that and create our operator. So we already have that. We're already creating this first part. So it's going to be 8 divide 2 times 3 plus 7. All right. Everybody's cool with that part? That was our homework assignment.
The operation.
Okay. Now we need our op stack and we need our output queue. So we will dequeue from our input queue, and we're going to look at it. Because this guy's a number, we immediately put it onto our output queue. We enqueue it to the end of our output queue. Then I will dequeue from our input queue. I'll look at it. This guy's an operator. Because he's an operator, I'm going to try to push him onto my op stack. Right now my op stack is empty, so I'm allowed to do that. So I will push him onto the top of the op stack. Then I will dequeue from the top of my input queue. I'll look at it. I see that guy's a number. What do I do with numbers? I immediately enqueue them to the end of my output queue. Then I will dequeue from the top of my input queue, and I will try to push him onto the op stack. But right now, it's a tie. Multiplication and division have the same strength. Therefore, I am not allowed to push it onto my op stack until I clear at least one thing from my op stack. So I'm going to have to pop from my op stack. And enqueue that guy to my output queue. Then I can try to do the multiplication again. This time it'll work. I am allowed to push multiplication onto the empty stack. So I will dequeue and successfully push. Then I will dequeue the 3. It's a number, so I immediately add it. I immediately enqueue it to the end of my output queue. Then I will try to add the plus on top of the op stack. Not allowed to do that. Multiplication is stronger. So I have to pop the multiplication, and I need to enqueue it in my output queue. Now I'm allowed to do the addition. So there's the plus. Then we dequeue the 7. We look at it. It's a number. So I immediately add it to I enqueue it to my output queue. Now my input queue is empty. I have nothing else to process. So my last step is to clear the op stack. So as long as the op stack still has stuff in it, I want to pop from the top and enqueue it to the end of output queue. Make sense? So forget about the stuff down here for a second. Are we good with our output queue right now? Everybody understand how we got to that point?
Can you go back just one step? So you pop from the top of the op stack, right? You pop the plus sign from the op stack.
Yeah, well, the last thing I got here was the 7, right? So I DQ'd the 7, noticed it's a number, NQ'd it there. Then I went to try to DQ again. Notice there's nothing else in input queue. It's empty. Because I'm done with my input queue, the very last thing for me to do is to clear my op stack. So that means I need to continue to pop off my op stack and NQ it to my output queue until it's empty. In this case, I only have to do it once. So I pop, and then I NQ it in output queue. So when all is said and done here, your input queue should be empty, your op stack should be empty, and your output queue should be the reverse Polish notation of your original. That make sense? All right, so now I'll get you started on the op stack. So we're going to create a stack here because our output queue and our input queue are the same. We already have functionality for that, right? We have a queue that knows how to hold ops and numbers. So we're just going to create 2 instances of that. Now we're going to have to write a stack with our push and pop. So I'll go ahead and add a class. And what we'll do here is for the, well, it's a stack, but it's a special stack, right? So we can call this an op stack because it has to play by those rules where we're not allowed to just haphazardly push onto it. Does that make sense? So we're going to go ahead and name this guy op stack because it's not a general purpose stack. It functions like a stack, but it's similar to our towers from Tower of Hanoi. So there's our op stack. Yes, I'll add it to my repository. Okay, so this guy is going to have, this guy's only going to have op nodes in it. So I'll have a private op node top. I'll also go ahead and create a private int called count. That might, actually, you know what? We're going to give ourselves a peek. I think that'll be a better way of doing this. All right, so now we'll have our constructor for this. So public op stack takes no parameters, and we set this dot top equal to null. Then we'll go ahead and create our public op node peak. This guy will return this dot top. We'll have our public op stack, or I'm sorry, op node pop. So this guy will remove from the top of the node only, top of the stack only if there actually was something there, and we'll return that value. So we'll say op node cur top is equal to this dot top. Then we'll say if cur top is not equal to null. If I actually have something up there, then we need to actually disconnect it. So we're going to say this dot, not this dot, we'll say cur top dot set next node to null. That will disconnect it from the top of the stack, but we need top to point to that guy's next node first. So we'll say this dot top is equal to cur top dot get next node. So the new top will be the very next guy in there. All right, and we know that that guy is going to come out as a op node because we happen to know we're only going to be dealing with op nodes here. All right, so we'll update top. We will remove pointers from cur top, and we will return cur top. All right, so that's pop. Finally, you're going to have public void push. You actually might want to create this as a public Boolean push, so you can find out whether or not it works. Or you can just look at peak to determine whether it's legal. You can decide. Okay, so public void push. This is the logic for whether you can show or whether you can add a op node to the stack. Make sense? All right, so your homework for Thursday is to create your, we've already created the input queue, so create the output queue and create the op stack and do the shunting yard algorithm up through the reverse Polish notation. So maybe show those, you can either print them out to the screen or you can show them in your interface, doesn't matter to me. But clear out your input queue, clear out your op stack, and ultimately produce an output queue with your input in reverse Polish notation. Make sense? All right, I will see everybody on Thursday. Remember today, student, faculty, staff Bible study. God and grub. Go to the cafeteria, sign in, get a free lunch, then take your tray down to the terrace room. And that goes from noon till 1. Or noon to 12:55.